Okay, so we're going to talk now about inverse matrices. We'll start with a definition. A matrix B is an inverse matrix. It's an inverse matrix for A. This original square, you'll notice, by the way, matrix A. If when you multiply them in either order, as I've got indicated here, you get the identity matrix. Now, we've seen previously that the identity matrix plays a role as far as matrix multiplication goes. That's kind of like 1. You multiply it by anything, you get the same thing back. So in that this is playing a role kind of like a 1, you can see that what we're calling here the inverse matrix is playing a role kind of like a reciprocal, and thus a multiplicative inverse, and thus the choice of terminology. Okay, so that's the definition of an inverse matrix. Here's an example given this matrix A. This matrix B is an inverse, and you'll notice that A times B in either order, whether B is on the right or whether B is on the left, in either case you do get the identity matrix as the product. Okay. All right, a little bit of terminology. If there is an inverse matrix for matrix A, we say the matrix A is invertible. Natural choice of terminology. Okay. All right. So a theorem about inverse matrices, and this is something which at a glance may seem obvious, but it's not. And what this theorem says is that if you have an invertible matrix, then the inverse is unique. In other words, there's only one inverse for an invertible matrix. Well, certainly that's true for real numbers. And that's why this may seem obvious, but we have to acknowledge that matrix multiplication is not the same as real number multiplication. So this is not immediately clear that there will necessarily be a unique inverse. How do we know there aren't multiple inverses? So the proof is lovely. Here we go. Suppose we have 2 inverses for some matrix A. So B and C, 2 different matrices, both inverses for A. And our goal, keep in mind, is to show that the inverse is unique. So our goal then is going to be to show that B and C must be equal to each other. All right. This is a clever proof. We're going to start by considering something that's not immediately clear we're at all interested in. In this case, this particular product, B times A times C. Not clear at all why we're interested in this. However, note the following. First, we observe that we can do the left multiplication first. Right? Multiply B times A before we get around to multiplying by C. This is using the associativity property of matrix multiplication. Of course, B being an inverse for A, we know that BA is the identity. And of course, the identity times anything is itself. So on the one hand, this expression that we don't seem to care about is equal to C. On the other hand, you can group it the other way. Again, matrix multiplication is associative. And because C is an inverse for A, I know that AC is the identity. And of course, the identity times anything is that thing. So this thing that we don't seem to care about, the nice thing about it is, on the one hand, it's equal to C, and on the other hand, it's equal to B, and therefore, B and C are equal to each other, and therefore, as required, these 2 inverses that might exist, they have to be the same, and therefore, the inverse must be unique. Okay, lovely, clever little proof. All right. Now, here's another issue that we have to worry about. And this is actually a beneficial result. Not so much a worry, I suppose, but this is a neat fact about matrix inverses. Notice that for a matrix to be invertible, it does have to be square. Okay. And that's a condition of this theorem. If you have a square matrix, and suppose that AB is the identity. So now it's tempting to say from this that, starting with a matrix A, it's tempting to say that if AB is the identity, well, gosh, it's playing a role, B is playing a role kind of like a reciprocal, and doesn't that mean it's necessarily the inverse? Well, that's not the definition of an inverse. The definition of an inverse is that AB is the identity and that BA is the identity. Now, these are two different statements, right? So really, we have to check both. As it stands, we have to check both of these are equal to the identity in order to truly conclude that B is an inverse. What this theorem does for us is it says that if you have the one side, in other words, if AB is the identity, then it must be also that BA is the identity. In other words, this theorem says that we don't really need to require both of these separately to be true. That if either one is true, the other must be true. So this is a nice theorem to have. Let me start by showing you what I'll call a bogus proof. So in other words, this is not a valid argument. It's very tempting. So keep in mind we're starting off with AB as the identity. And now I'm going to left multiply by A, right multiply by A on both sides of the equation. That gives me ABA equals IA, which of course is A. All right. And now, how about I cancel on the left? Well, what I end up with then, it would seem, is BA equals, there's an identity over here in effect. You cancel the A and you get BA is equal to the identity, and it appears that we've gotten to what we want. So this is a very tempting line of reasoning. And it is not allowable. This is not valid reasoning. We committed a crime here, and I kind of swept it under the rug as I was doing it. But in particular, what I did is I just did a cancellation, right? We can't just cancel. We saw last time that canceling is something that has conditions. There's strings attached. You can't just cancel anything willy-nilly. In order to do a cancellation on the left, in particular, go back a couple of pages in the notes. In order to do a left cancel, like so, the matrix has to have the uniqueness property. All right, so before we can do anything like this, we have to first show that A has the uniqueness property. Okay. So, here's what we know. I'm going to start with this assertion that this system always has a solution. Not immediately clear. Now, how do I know that this system always has a solution? Well, I'm going to show it always has a solution by explicitly finding the solution. And this algebra here, we'll see in a moment, actually demonstrates this. Now, first of all, let's follow through this algebra. This product is equal to that product. AB is the identity by assumption. We're given that AB is the identity. And therefore I get C. Okay, now, so this is just some algebra, but now let's reinterpret this as a statement about a system of equations. This says that BC is a solution to this system of equations. You just, look at exactly what that says. So how do I know that this original system, how do I know that this always has solutions? Well, because here it is. There's the solution. BC will always work. Okay. All right. So that system always has solutions, and therefore its coefficient matrix, you recall our terminology from earlier, that coefficient matrix has the existence property. Okay. Now we've proved neat things about the existence property. The existence property means that there's a pivot in every row of the reduced row echelon form. Now, don't forget our matrix is square. So if there's a pivot in every row, that means the number of pivots is equal to the number of rows. Well, if the number of rows is equal to the number of columns, that means that the number of pivots is equal to the number of columns, and that means there's a pivot in every column as well. So, immediate consequence of the fact that this is square, a pivot in every row means there's also a pivot in every column, and that's what gives us then the uniqueness property that we needed. It's a long way to go, it seems, to get this one little detail, but it's a critical detail that this matrix has the uniqueness property. Okay, and now our previous algebra works. Here's that previous algebra again. You start with A, B is the identity. This is what we're given. Right multiply by A on both sides. Right. Move parentheses around a little bit to get this, and now we can indeed left cancel because the matrix A does have the uniqueness property. We just showed that, so that cancellation is now legal, and therefore BA is the identity as required. That proves this result.